So let's start. Let's start our algorithms lecture, and we have a practical assignment. So to solve a crypto arithmetic puzzle, send plus more money. And again, it's basically just like a, well, replacement game, you could say, mathematical game, right? So how would we solve this, right? So we were talking about different approaches. So the simplest approach, and again, in most problems, start when in doubt, use brute force. That's the saying, right? I forgot who said it. When in doubt, use brute force. I believe it was one of the Unix guys who solved it. Ken Thompson, yes, he's one of the inventors of Unix in the late 60s, right? Basic idea is, if you know, it's a good starting point. A full search, maybe just go through everything, right? In this case, right? So we will see about solving it. In fact, I heard you have a solution, right?
Yeah.
Okay, we'll look at it. But again, maybe first, but for fun, we could also try to solve before we look at the brute force solution. How would we solve it as a humans? That's another approach, the other end, like a really selective search. Maybe we could look at that as well, right? So maybe, because then we can compare it actually with the solution. So what I'll try is, actually, I'll see if I can get a paint, and let's see if I can do some paint solution, maybe so I can, let me open a paint. Or do we have paint here? Actually, let's do something like that. See if we can solve it. I think we do have. We'll look at my amazing painting skills, yeah. I'll do that and see if this works. Right, because, yes, so send, right? Yeah. So send more, and we have money, right? Plus money. Right, so as a humans, right, of course, it's been a while since I solved these puzzles, but basically, right, so how would we solve, from which end do we solve it? What's the approach? How would you solve this?
First of all, m has to be 1.
Exactly, that's what I was going to say. Yeah, if you are a human, you look at this m, right, here, right, so m, right, obviously has to be 1, because when you add two digits together, right, you cannot get more than, you know, something, one something, or maybe a single digit result. You cannot get 20, right? Out of, you know, 9.
This is 9.
So, okay, so this means this has to be 1, so then it follows, right? The only way, exactly. So I'll do this, try to do this here, right? So I'll start writing solutions. So 1, right? And again, I'll be using, I don't, so this is 1, right? M, right? So this means S has to be 9, right? No other ways, right? So S, right, has to be 9, because that's the only way we can go from 1 to, we can jump over, right? Have a carry digit, right? So let's do that. So M is 9, right? And for S is 9, sorry. Okay, and now here we come to an impasse a little bit, right? So 9 plus 1, right, that's 0, right? So it's very tempting, and I don't, like I said, it's been a while since I've done this puzzle. So is this actually 0? That's a good question, actually, right? It's very tempting to say, okay, yeah, this must be 0, right? But it's not necessarily true, right? Why?
Because
it's possible we have a carry here, right? It's possible we have a carry. So it could be, well, what kind of carry could we have? Well, if you think about it, could be only carry here would be 1, right? We cannot have 2.
No, it has to be 0.
So it has to be 0. Why? Because we already, by law of exclusion, right here, 1 is already taken, right?
Yeah.
So 0 has to be 0, which is also very easy, right? So 0, 0. In this case, it seems like we're doing a really good progress. So we have 1, 2, 3 digits already. Send more money. And we have E, right? We have E, very tempting. So there's no carries, right? So, but what we do know, look at this here, E and N, right?
They have to be the same, but they can't be the same, so there has to be a carry.
There has to be a carry here. There's a carry here. Well, again, in this case, since we only have 2 additions, right? This means only maximum carry is 1, right? So N plus R, or, you know, gave us something. So this is 1 for sure, right? Guaranteed. So E plus N. So E So n is basically e plus 1, basically. We know that much, right? We could say for now, all right, so n equals e plus 1, right? That's much we know. So it could be 2 and 3, 4 and 5, 6 and 7. Well, that's it, right? 7, 8, technically, right? Okay, so far. What else could we do? Maybe there's some other things, some other constraint. What other constraint is there? Let's see, so e is here. Right, there also have to be e's. We have a bunch of e's here. There's e here as well. Let's think about it. Is there anything with parity, meaning odd, even, maybe things like that we could think about? I'm right now. I'm just drawing a blank at the moment. Right now, what we've done we made a quick progress, right? But is there anything else we could do here, as humans, right? We have to start actually backtracking now, right? Actually start just plugging in numbers. We could do that, right? But let's see if we can logically think of some restrictions here still. So we have 2 more digits, right? So e and maybe start at n. I mean, if of course
R has to be 8.
Okay, why?
Because since e is by 1 smaller than n,
yeah,
R technically has to be 9 in that case for e to be for e to be less than 1 by n, and there would be a carry.
Oh, right.
9 is already taken. That means there must be a carry from d plus e equals y, and R can be 8.
So you are saying R should be 8. Okay, let's do this. Why? So if it's 8, because to get carry, right? Because otherwise if it's 7, what would the problem is 7?
And there would also have to be carry on that.
Yeah. Okay. By the way, this is all you think. Do you think there's carry here as well?
Yes.
You think so? Okay. All right. Yeah. Because okay, you see, I'm at the moment, right, I'm not sure is this carry needed, because you have d and e and y, right? 3 different numbers. I mean, it's possible that 2 plus 3 is 5, for example. I don't know. I'm just saying, right? So possible. Okay, but let's try this. Okay, we can plug in 8. See if this actually leads us to solution. So does it lead to the solution? Yes. Okay. Good. Okay. All right. E. Right. We still have this little equation. So it'd be 6 and 7. So what can we try? Oh, we have 2 ends. We have 2 ends, by the way, right? Okay. So, and that is a little bit tricky. So if this was, let's say, we have en and ne, right? So let's say if this was, how do we get 4? Let's say this was 4. Yeah, that's interesting. So if this is 4, okay, we get the carry. If n was 4, then n has to be 3, right? Okay, is that possible? I'm just drawing back.
What?
So n. So I'm just saying, okay, if this was 4, right? I don't know. It's probably not going to work, right? So we end up with what? We need a carry then, right? We end up with 3, right? And we end up with 1. Wait.
You have to 3 at top.
Oh yeah, of course, 3. Yeah, 3, and then we end up with 4. So this looks okay. I'm again.
Yeah.
And
then you have to also plug in 3.
3 at the
right
more.
side.
Here?
Yes.
Yes, we do here. And now the challenge is how do we get? We have 7. What do we have left? We don't have enough left. We need a carry, and we can't get the carry, and this is a problem, right? We need 7. Okay, if I plug in 7, right? We get 0, and that's not allowed, right? So that doesn't work, unfortunately, right?
E has to be bigger than.
So E has to be bigger, right? So Control Z, right? Control Z. I'm lazy. Control Z, Control Z, Control Z, Control Z, Control Z, and Control Z. Okay. Right. So.
You can put the carry on the second one.
Yeah, let's do carry again. All right. So 4 and 5, right? So again. Let's do it one more time, right? So this would be 5, right? Same approach, right? So we want 4, right? We get 4 here, right? And we get 1 plus 1, 5, 4, right? Again, and E is 4 here. And that looks much better. And now, nope,
No,
again,
that doesn't work.
7, right?
Yeah, E
And-
has to be 5. Yeah. And then-
Okay.
So Y can be 2.
Yes, so the problem, we need to get a higher number here. Okay. All right, one more time. Control Z.
Y is 2.
So we're backtracking. Okay. So we got to 5 and 6, right? 5 and 6, are you saying, right?
Yeah, yeah.
So and 5, 6, 5, right? And 6, and this is 5, right?
5, 7, 2.
So 7, this looks very good. So which numbers do we skip? We skip 3 and 4, right? Yeah, we skipped 3 and 4. So again, yeah. So this is a solution, right? It looks okay to me. Yes?
Yep.
And this is actually your brute force came up with this as well?
Yep.
Okay, so the question now, of course, is there any other solution? Could there be? I mean, we didn't try 7, we didn't try this constraint, right? We could have tried, bless you, so we didn't try 6 and 7. Would it have worked? Maybe not, right? I didn't want to try it. So your brute force only found 1, right?
Yeah.
Okay, all right. So okay, so we saw how the humans would solve it, right? But again, computers, again, we could try to come up with this, try to make up these constraints. I mean, this is something similar we could do it if you want to optimize this type of problem, right? Add some extra constraints, right? But for now, right? For now, we will want to do actually solve it, right? All right. So let's look at a brute force solution, right? Let's see. What. So Edwards, you sent in, right?
Yeah,
All right, let's take a look again. So, one submission, very good. Some lazy, I know. You have, but I'm giving you a little extra time to submit it if you want still do it afterwards. Okay, let's see. Very good. Money DFS, depth first search. Right, I'll save it. And I will open it up in a notepad. Or hopefully there's something better than notepad. Okay, Notepad Plus. Okay, notepad. Alright. So thank you, Edwards.
Oh, yeah.
Alright, so this is this.
Oh,
Oh, let's take a look at this solution. So, alright, you have main, alright, hard coded, that's okay. Again, make it work, right? Too many unique letters, right? You check if there's actually if it's a sanity check, so to say, right? I'll make it a little bit bigger so you can see, everybody can see this, right? Pretty nice. So unique letters, right? You make a list. Use digits as set, right? Letter to digit, right? Basically, if there's no solution, right? So, word to number. Let's see what happens here. So, you create an integer out of all the digits, right? Letter to digit for letter in word. A stupid question. Why did we do this? Oh, wait.
Just join.
Oh yeah, you're joining. Yeah, you're joining. Okay, got you. You're getting it a string from the digits, right? And then you're joining them back. Okay, got you. All right, and then you're going back, right? Yeah, that makes sense. Word number, very good. Is valid solution. So now that's of course the key part. You create word to number, very nice. Word to number, again, and basically, is this a valid solution? So again, so this time of course you're putting all the digits, right? So this requires that all of them are filled out, right?
Yeah.
So yeah, so this is basically a brute force solution because you have to have all digits, right? All right. So DFS, unique letters, you try to fill it out, right? If index is length, unique letters, right? If index was, if solution found, return true. Else, of course, we return false, right? So, and now, let's look at our assignment, right? Current letter.
Yeah, because this is a recursive solution.
Yeah, it's a recursive solution, right? So, oh yeah, there it is. There is our friend recursion, right? So is our so this is our this is our base case basically.
Yeah.
Yeah. Yeah. Okay. And you start assigning. So the beauty, of course, again, of why recursive solutions are nice for backtracking, of course, because, well, you get all the stack for free, basically. I mean, for free meaning you don't have to keep track of it yourself. Recursion does it for you, basically, right? So you keep trying, right? So all of this is done. So basically backtracking, right? Of course here, right? And you remove the digit. Okay, looks very good. Again, of course, we could trivially change this to parameters. That's fine. We'll do that later. And let's see if it actually works, right? The big test. The big test. Okay. So send more money, right? So R, right? This is exactly what we did, right?
Yeah.
Yeah. Very good. Very good. All right.
I have a question.
Yes.
With a random solution, like, I think it would be the same efficiency as any other. Like,
Well, random meaning
like we would just randomize the numbers.
Oh yeah.
I think it would be the same efficiency.
Yeah, 6 seconds. Well, the thing is, well, of course, you don't. Hopefully, didn't mean randomly trying numbers, just throwing them out, right? No, not like that. Not Bogos sort type. Not that approach, right? But no. Yeah, which ones to start? Okay, so you're asking whether we should start, like we saw with the other puzzles, right? With the Sudoku, right? Or now also with the queens, right? Whether we should start, you know, from 1, right, or from n. So let's see. You have this part here. This is where you're doing the assignment, right? This is a search, right? So you could do reverse, right? You could try reverse, right? And this doesn't cost us anything extra, right? This should work, right? Let's try this one more time. 6 seconds. It should work. Let's see. Reverse range. I don't know. No, 0.7. Much faster. Much faster. 5 times faster, right? Looking the other way. But again, of course, you don't know that ahead of the puzzle, right? You don't know which way, what kind of evil solution maker, you know, if they know what kind of approach you're going to take. Of course, I think that truly, if you want to completely prevent any type of attack on your solution, right, you would make it randomized. Basically, here you generate digits in a randomized set, basically. But the question now, of course, is that you got to be careful now. It's going to work in in your backtracking. Are you going to maybe miss some numbers? It's a little bit of, you know, offhand. I'm not sure right now. Okay, but yeah. So reversed actually, right? So again, all right. So this actually, of course, is actually slower. So in this particular case, right? So in this particular case, here it turns out, oh yeah, that reverse is about 5 times faster, right? Again, so okay, very good, right? So you hopefully, so this is basically a full, well, very close to full permutation search, right? So let's see. Again, so who is doing the math for possibilities? Right? So we have 8 different. We have 8 symbols, right? 8 letters, right? There's some extra constraints. So what are the probabilities actually, right? Who was doing the? You said the 1.8 million, something like that. You came up with. I'm curious how you came up with that number. So let's see.
9 times 9 times.
So yeah, so this is 9, right? So let's see how much full brute force would take. So we have 8 unique letters. That's permutations, right? Wait. Okay, so 8 unique letters, right? But we have 10 digits. It says 600,000, right? Pick 10, 8 out of 10, right? That's very close, but it's actually less because you have more restrictions. Actually, I'm not sure about this number. It looks okay to me, but you have to calculate. You can't trust the AI. Actually, it is a bit less since first two digits cannot be 0, right?
Yeah, it's 9.
Me?
Yeah.
Yeah, 9. So it'll be 9 times 9
Times 8.
and 8, yeah, and so on and so on and so on and so on. So yeah, so it'll be, I guess, so not too many, right? The brute force is actually pretty quick, right? So it should be pretty quick, right? Yeah. So how much? Yeah, 9. Okay. Smart AI, right? 3, 4, 5, 6, 7. Okay. And I'm again, remember AI, we didn't used to do the math. So are we gonna trust AI on the math right now? I don't. But I imagine it has what it's doing is really cheating. It's running a Python program to do it, right? So we will do the same, right? So let's trust it. Trust but verify. Right. So yes. No. Let's do that. And we will do this, right? We'll do tuples, Control C. Alright. Alright, comma, right? Alright. Now. So you see, trust but verify. Don't trust blindly this AI. So we had what 1.6, and this is slightly less, like 1.6 million is the actual true. This I think is the actual answer, right? Right. So fake. Right. So right. So verify. To do verify. Thank you AI for making it myself not trusted. Right. So this means so is, but still that's this. So is the actual number we need to test in full brute force, right? So why? So do you think we checked all of them here? Well, no. I mean, this was a full. We were always checking full solutions, right? Full permutations. But of course, we didn't check 1.6 million, right? What we can do is, let's do again, I'll do a global counter, right, since I'm lazy, right? And we can check how many, right? Again, I imagine, right, it's going to be probably a couple 100,000, right? So 0.7, right? I'll do a global counter, which is kind of silly, but still, calls. We want to basically have how many stack calls, right? So, yeah, then we could pass it. So this is not, of course, global counter, right? 0, right? And count, right? So global counter. We'll do this basically, and check here if it's one like index length, and here I'll see how this works. Global counter, right, and counter plus 1. Yep, exactly. All right. We took number iterations counter, right? And again, let's see if this works actually. Hopefully this I did it correctly. Yeah, 240,000. So now, how about the other way, right? How about the direct way? So it was 6 seconds, so about 5.5 times slower. So I imagine it's going to be about million something, right? Right? Again, it always makes to make follow along if this makes sense. If it doesn't make sense, of course, we can regress. So let's take a look. Oh, other than make mistake in typo. Oh, there's yeah, because this is reversed. Okay, let's do it one more time. 6 seconds, maybe a little bit faster. Depends how busy the servers are. But yeah, 5.9. Yeah, wow, 1.9 million. So what's happening here? How come we got over that? That's little. Maybe there's the counter actually was too. Where's our counter? Here, right? Or maybe, well, this is 0, right? Because I ran a cell, right? Seems a little bit too high, right? So this is actually, yeah, 1.6, right? 1.8 million, right? And we actually got 1.9 checks. So maybe we did something, there was some duplication maybe. Maybe we did like actually, we run something which is not, well maybe, or maybe the order method, or the order doesn't matter because, I mean, we don't really, right, we just have a mapping, right, how we, let's think about this. 1.9, right? So it seems like either we did probably check something a couple times, maybe because again we don't have memorization, right? We are not doing, we're doing the, you know, check maybe from different, how should I say, we checked, apparently checked something twice, some few hundred thousand permutations, right? Okay, right, all right. So let's go back to our reverse solution. And yeah, again, so it's 240,000. So that of course looks good. So now, okay, well let's do one more brute force, and I think we can use just a complete lookup, right? From iter tools, Python offers us iter tools. Right? We won't have time to do. Let's do one more time. So now down full permutation search, right? Right. So let's do that. So we can use, yeah, let's see if this works. No, let's make it. Let's see if we can build it. Let's create the following brute force solution that would be universal for any two-word sum into third word, right? So we will use iter tools, right? Exactly. This is really nice, handy. Maybe handy on your, if you need something, you know, just get everything, right? You don't have to do it by hand, right? Save you some time. All right. So let's see what else do we need. Yeah. All right. So simple import iter tools or import permutations. And now define. Brute force, right? Let's see if this works. For permutation, iter tools, permutation range 10, right? So num1, num2 result. Let's see if this works correctly. Letter to digit. Letter to. Let's see if this works. Okay, digit. Oh, okay. So letter. And let's see zip. Let's see what's happening here. Okay, we are going through what? Letter digit. Okay, let's see, we are zipping permutations and numbers. Okay, so how, this is not gonna work yet. No, this is two AIs, okay, because what's happening, of course, we are doing what? We have the permutation, that, you know, 10 digits, and this is not what we want, right? This is basically the 3 strings together, right?
You need a set at least.
Excuse me?
I mean, you can make a set and then.
Yes, exactly, right. We need to. Okay. So we basically need to permute basically the numbers. That so that digit. So this is not valid. So we can check this is not valid, right? If it's valid solution. All right, it's using the. Well, it's using the. Is valid solution? Where is it? It's your
yeah.
It's using your code, right? This one here, right? Okay, this one is okay, but wait, let's see if this works. Actually, word number, it might actually work. Let's take a look. I don't know. I'm not sure. Let's see. This is gonna be num1, num2, right? Let's take a look. It's kind of crazy if this works actually because it's using reusing your code actually. This might actually work, but let's take double check, right? Right. Well, right. So no solution, and of course.
Maybe it won't work.
I don't think it will work. I think no. The zip. Okay. So it has all the digits, but it's not. Letter digit for permutations because you have the numbers because it's gonna stop. It's okay. You need a set here, right?
Yeah.
You need a set.
And then convert the set to a string.
And the thing is, of course, the thing is with sets is you want them to be that sets have this annoying property It's well, the Python sets, it's not an annoying problem, it's not ordered, right? So the question is going to be always deterministically same. I'm not sure, we'll try. Let's try this, right? So set of this, right? So I need set here, right? That might work. I'm not 100% sure, right? And we are zipping them together as pairs, right? That's possible, right? Because remember, you have only 8, right? You only have 8 uniques, right? And of course, questions are again, why should I do this here or each time? I could do it separate, do it here, right? You agree? I should do it here, right? Unique letters, right? And I can add it here. That makes more sense, right? Are you guys following me or not? Some of you are, right? All right. Now, it will try all different permutations, right? This is again completely blind, even not looking at zeros, anything, right? And we'll see if it actually finds a valid solution. This one here, right? Again, letter digit. So this might work or not. This is.
Don't think so.
Okay. Okay. Are we ready? I don't know. It's gonna. Not ready. Solution found. But it's solution found. However, it's silly, right? So because there's 0, right? There's 0, right? It did not check for the leading zeros, right? So, so the question is now, how did you get around this problem here? How did you avoid this? You checked somewhere here, right? Where does it check? How did you avoid the 0 part? Or did you just get lucky as well?
Go down a little bit.
There. Here. Oh, here you go. Yeah. Okay, there it is. Very good. Yes. So basically, we need to add this part here in this brute force solution, right? So this is what's the big difference between these two solutions? Of course, is they're both basically full brute force, except this one is iterative, meaning no recursive calls, right? Because I think this one is valid solution. Both number, those are not recursive, right? So this is iterative, loop based. Yeah, loop based approach. Again, on your midterm, you can use either approach. Again, recursive might be maybe you can start with recursive, but again, iterative might be fine. But then, of course, here we need to check, right?
In the same if. Oh.
Here, probably.
Yeah, you can do it in the same way.
Yeah, or should we do earlier? Let's do it earlier, right? That might be better, right? Right. So how do we check? So if well, how the heck do we do that? How do we check? How do you check this first? Oh,
You can go down.
no,
You can just check if permutation. Oh wait,
no. We need these We need basically this. I mean, first,
Yeah.
right? So how do you do it here? Let's see. Num 10.
Yeah.
Right, because you were assigning, right? So, okay. Yeah, we need to check. So if, because we have the assignment, right?
I think you can
Yeah, yeah,
just
check
check the dictionary for number.
Yes, yeah, okay. So letter to digit, right? Yeah, okay. So we need to check, yeah, if, let's check first digits for 0. Right, letter to digit.
Yes.
Yeah, this will work, right? Yeah, no, not 0. And of course, this is not even necessary. This is like this is optimization. So this is sort of we break a little bit of we sort of cut down we cut off the full search a little bit early. So that's slight. It might make sense, right, for some more difficult problems. So this is a constraint. So this is one of our constraints, right? One of our constraints, right? So again, this is an overkill, right? Because letter digits is not necessary. We just check for the string, right? It's the string 0, right? But okay, all right. We'll leave it in for now, and let's see if this finds an actual full solution, right? Are you guys, everyone else with me? We're gonna. Oh, now it's gonna break. 6 seconds? 6 seconds? No! It keeps looking. Worse.
Oh, it doesn't work. Oh.
It found it. So it found it, right? So it found it, range, right? And of course, what we could do is, we could do reversal, right? Again, let's try that. Let's try our old friend. Alright. And here we could, the beauty of this, of course, we could count how many times we try here, as well get a counter, right, next time. Oh, like that. That was great. 1.7, so, well, again, yeah, so about 5 times faster. Of course, the cursor is more faster, right? So again, counter, right? Counter, right? 0, and I'll do here, right? And return false true counter, I guess. Right. If not, oh no, I had to check. Okay, I'll just return false. Of course, right, I'm here. Yeah, all right. This is of course not very good code, but okay, that's fine. Let's do it one more time. So of course, 400,000 now, right? So again, the way it works, because of course we get all these false ones, right? Also, how about the worst one, right? Let's do this one more, last one before we go to break. And I'll do this one here. So this should be about like over 2 million, right? I'm assuming, right? How much? Yeah, 3.2 again. But here we know for sure there's only 3.6 million, right? This part here guarantees these permutations, right? Is going to guarantee us the 3.6 million mark, right? So we're almost end, right? Okay. So again, what did we learn from today, right? So that again, the fact that searching order could matter. What I would have to like is possibly check some extra constraints. So the challenge, right? This remains open challenge basically. Challenge, right? Challenge, check partial solutions quicker, right? Quickly, right? To further optimize our solution, we would want to check partial solutions, right? Quickly, and then backtrack. Yeah, so that's the thing. So that's with the challenge, right? All right. But hopefully now you should be able to code a brute force solution. So what will happen, of course, on a midterm, if there's this kind of problem, brute force solution will give you maybe like 6 or 7, basically, right? So without any optimizations, you just throw something at that wall and it sticks, right, until it sticks, right? That will give you maybe 6 and 7, depending on how hard the problem is, right? Sometimes, it might be, give you even 8, right? Depends. So, but of course, if you see show any type of optimization, of course, that will, raise your grade, right? So, all right. So I'll add this to our repository. Send more money. Yes. My paint, right? Send more money, right? Okay. All right, so thank you. We'll continue at 11:10.